All right, welcome to the next video accompaniment for Chapter 12, Section 1. We're still talking about fundamentals of graph theory. I know there's a lot of videos about this, but that's because, well, there's just so many terms and definitions that go along with graphs, and I didn't want to make an hour-and-a-half long video. In this one, we are talking about the complement of a graph. And so in order to understand that, it's going to be helpful to understand what's meant by a complete graph. And then we'll use that to talk about what a complement is and how to compute the complement of a graph. So we already have this term complement as it applies to sets. Remember, a complement of a set is all the items that are missing from the universal set. And so that'll be similar here with graphs. And as well, we'll want to understand this relationship between the degrees of the vertices, the size, and the order of a graph, and how that relates to the same parameters in its complement. All right, let's get started. So first off, what is a complete graph? So remember, a graph is a set of vertices together with a set of pairs of vertices. So a complete graph is one where all of the possible edges are included. It has all the different pairs of vertices in it. So for example, if my vertex set is the elements 1, 2, and 3, then if I want a complete graph on these vertices, I want to include all the different possible pairs. So 1, 2, 1, 3, and 2, 3. And so that would look like, so here's my vertices, and then 1, 2, 2, 3, 1, 3. So we've included every possible edge in this graph. What about on 4 vertices? So in general, right, we've already talked about isomorphic graphs. In general, there's only one way to have a complete graph on a given number of vertices. So this is the one for 3. This is order 3. For order 2, the only graph would be this one. For order 1, the only graph would be this one. Let's look at for order 4. So I'll draw my 4 vertices, and then I will connect every single pair of vertices. So I'll connect every single pair. And this one has size 6. And let's look at 5. Let's get all 5 vertices drawn, and then every pair of vertices is connected. So that'll look like one like this. And then I also want all of these. So notice there's no other edge that I can put in here. This time our size is 10. And so we can think back to combinatorics, how many edges are in a complete graph of order n. So we call the complete graph of order n, we call this Kn. That's our notation for this. So this is the complete graph. And we understand that means that there's only one isomorphism class of complete graphs of a given order. And in general, if this has order n, which it does, this will have size. Well, I want to include all possible pairs, and these are unordered pairs, and so that would be, the size should be n choose 2 in general. So that's number of edges in a complete graph is always n choose 2. So here we see size 10. This is the same thing as 5 choose 2. 6, this is 4 choose 2, and so on. So that's what a complete graph is, and that'll help us understand what complement is. So the idea is a graph and its complement, if we sort of stick them together, we get a complete graph. All right, so I like to use this example a lot. So here's a graph. I'm going to draw it unordered because complements, it doesn't really matter what the vertex set is, what the edge set is. The complement can be done on isomorphism classes, so I'm just going to leave this unordered. So here's my graph G. G complement then, it's all of the missing edges. So in the background here, I have the complete graph on 4 vertices, which I could draw as this, or I could draw it like this. How else can I draw a complete graph on 4 vertices? Well, I could do something like this. Notice that's an equivalent way to draw the complete graph on 4 vertices, that these two graphs are isomorphic. And so I just want to think about what are all the missing edges here in G. And so in particular, I see this edge could be there, but it's not, and this edge could be there, and it's not. And those are the only two that could be there, but aren't. And so I'll draw that. So the complement, denoted with the overline on the graph, it has the same vertex set as the original graph, and it switches the edges for non-edges and non-edges for edges. And so anything that's an edge in G will not be an edge in G complement, and everything that's not an edge in G will become an edge in G complement. So notice here, I'll draw the non-adjacent pairs of vertices inside of here as well. So there's my original graph, and so they switch between each other. Let's maybe take a look at one other example here. We'll do one on 5 vertices, so we'll increase the order a bit. I'll call this one H, how about? And I'm going to do unlabeled again, and maybe H will be what's called a cycle graph on 5 vertices. Talk more about cycles in the next section. And then how to compute H complement. Again, I'm just going to draw all the missing edges. So over here in H, I could draw those sort of on top of H. I'll use dotted lines to make sure it's clear that these are not edges of H, but rather non-edges. And then over in H complement, so same, oops, I want to use white for the vertices. So same vertices, same vertex set, but now I'll just draw those missing edges. So that would be H complement. Now these two have a very special property in that, so notice H complement here, I could sort of redraw this. This is isomorphic to, if I just sort of move around the vertices a bit, I obtain, it's still a 5 cycle, right? I can go 1, 2, 3, 4, 5, and get back to where I'm started. And so again, it's actually the same as my original graph, so this can happen. In this case, H is isomorphic to its own complement, and we say here that H is self-complementary. And those are going to have some special properties. They're not always going to exist of any type, of any order. We'll see some problems like that in the homework. So that's what a complement is. So I'd like to figure out what is the relationship if you know G has order n, size m, and these degrees. What will G complement have? So, or how do these relate between a graph and its complement? These parameters. So if G, let's say G has order n and size m, so n vertices and m edges, and say degree of vertex vi. So let's say G has vertex set v1, v2 up through vn. So those are my vertices, and we'll say the degree of vi in G. So if I want to specify what graph I'm talking about the degree, if a vertex belongs to multiple graphs, I'll put a little subscript under the degree. So let's say the degree in G of vi is, let's call it ki. So that's the degree in G. Okay, so in G complement, well, G complement, because complement, we keep the same vertex set. So G complement has order n. And what about size? What can I say about size? Well, I know that G complement has all of the missing edges that G has, and missing in terms of the complete graph. So the size of G complement then, so what's missing from G? If G has size m, then G complement will have size n choose 2, the order or the size of the complete graph, minus how many edges were in the original graph. So in general, that formula will always work for the size of the complement if we don't want to count them up, say. And then the relationship between degrees of vertices. Well, I know that in the complement, or sorry, in the complete graph, every vertex has degree 1 less than the order, would have degree n minus 1 here. And that's in the complete graph. And so when I take the graph and its complement and kind of put them on top of each other, I get the complete graph. And so that tells me that the degree in G of VI plus the degree in the complement of the same vertex, that these should come together to give me n minus 1, which would be the degree. This is the same as the degree in the complement, or sorry, the degree in the complete graph of that same vertex. And so that's the idea here. I guess I didn't need to call that Ki. I'll just use this terminology. So maybe let's look at one small example of that. We'll do it on three vertices. So here's going to be my my original graph G, and then we'll look at its complement over here. Will just be these two connected and this one isolated. So notice, for example, I'll write down the degrees of all the vertices. This is degree 1, degree 2. And so here n is 3. And so the sum of the same vertex in the graph and its complement should add together to give me 2. And that's true. So that has degree 1, this has degree 1. So that pairs with the 1s over there. And then this one would have degree 0, or 2 minus 2. We can see that this has size 2. And this one has size 1. You add those together, you get 3, which is the number of edges in the complete graph. So again, if I take these two and kind of put them on top of each other, if I superimpose them, I end up with this graph. All right, so that's the idea of a complement. We talked about self-complementary graphs. We'll have some homework problems about that. But these properties are important to remember, this relationship between the size of a graph and its complement, and this relationship between the degrees of the vertices. All right, that's it for this one. See you next time.